Why is the entrance region important and useful? Here's a drawing that enhances the feature of this entrance. I already sketched that in the beginning the fluid is not aware of the round cross section. The fluid rubs against the solid surface of the wall. All right, and the fluid is slowed down by the wall. The region in which the fluid is no longer free or unaffected is the boundary layer region. So boundary layer here, and now, so she left. I have visions that things happen behind my back without my knowing. Okay. I'm adding the feature in addition to the average speed of the m dot that comes in. There is, in fact, a temperature difference. The fluid that comes in is hot, of temperature, I said here somewhere, T at the inlet, and the wall is cold. And that means that there's a temperature distribution. Thank you, Hamad, for coming. Hamad is my most recent doctoral student, which is why he, look at him. He looks like the cat that just swallowed the canary. That's the way I felt when I defended my thesis. I felt no pain. For a very short while. After that, the pain returned in big time. And in the beginning, the hot fluid remains hot only in the vicinity of the center line. In other words, if you plot a temperature distribution across the channel, and I'm going to make the cheapest drawing of a temperature distribution across the channel. The first feature is that the core is hot, and that across the boundary layer, the temperature decreases from hotness to 0. See like that? You see that? And, it is this way, except that the hot core becomes narrower and narrower. And then at the expiry of the entrance, called capital X, the temperature distribution is no longer trapezoidal, it is triangular. It has a peak temperature here, and I should have made a better drawing. The reason for comparing these two temperature distributions is to recognize that the gradient of temperature of the wall is sharp. This is a gradient, meaning the slope here, sharp, as opposed to shallow. Sharp because the distance across which the temperature changes is small here. It's the biggest that it can be downstream. And that means that the heat flux that comes from the sides, this heat flux is equal to the thermal conductivity of the fluid times the, let's say, the temperature, the radius right at the wall. The heat flux is greater. It is actually the greatest right at the lip of the mouth of the duct. When you study heat transfer, or when you studied, you should have been taught that this heat flux decreases this way from infinity to something constant all the way to the end of the entrance region, beyond which the constant heat flux is the constant heat flux associated with the fully developed region. So this constant, easy to find in a textbook, but not very useful in practice, is the heat flux of the fully developed flow region. So if the flow architecture to which this duct belongs has the purpose of communicating heat transfer from the fluid to the surroundings, meaning through the solid in which the duct is embedded. So, and that means I'm walking you or sneaking you into chapter 5, which is about heat flow configurations. If that is the application, then the most useful portion of the duct is the entrance. That's quite revolutionary, because the entrance is almost never discussed in the heat transfer textbook, because it's complicated. All right, so for heat transfer applications, and something else, heat transfer design traditionally is taught with regard to heat transfer between two streams. Hot stream making intimate contact with a cold stream in a device called heat exchanger. Even simpler than that, but not taught, is the heat transfer between a stream and a solid. For example, a plate that's cold and with channels machined in it, you see. A solid plate like that is your laptop. The laptop, maybe not anymore, because by the older ones had a fan inside that pushed air through in order to keep the laptop lukewarm, not too hot. All right, so that is the stadium in which this kind of game is played. And how do the notions that I put on the blackboard last time change if I move the, let's say, spotlight from the fully developed region, which is the Poiseuille description, to the entrance? Let's find out. First of all, I'll sketch again in this region the T-shaped flow with which we dealt. It had the dimensions L1 and D1, that is length and the diameter L2 and D2. And now, in addition, because every channel is an entrance region channel, it has boundary layer thicknesses. Boundary layer thicknesses, and it's not just the entire sketch that's relevant, it's the thickness of the boundary layer at the place where at the location where the boundary layers meet. So this red segment is the thickness of boundary layer in region 1, in duct number 1. And then continuing, meaning flow comes in, flow exits. Continuing, there are boundary layers developing from this stagnation region outward. And then there is a second boundary layer thickness called delta 2. And from the subject of convective heat transfer, we can recognize the following things. First of all, these pink segments, delta 1 is the same as d1 over 2. Delta 2 is the same as d2 over 2. From a convective heat transfer, delta 1, meaning having to do with the extent of the entrance region, delta 1 is the boundary layer thickness given by a formula of this type. This C is a leading constant that's irrelevant here. And then the length L1, and then the Reynolds number in region number 1 to minus 1/2. And delta 2, similarly. And the Reynolds numbers are a shorthand for U1. U1 would be well, basically the original one that comes in. And then U1, and then D1 over nu. And then the Reynolds number in the branch is U2, D2 over nu. There's a relation between the Reynolds numbers and these capital U's stemming from the fact that mass flow is conserved from the stem to the branches. So from the obvious fact that m dot 1 equals twice m dot 2, m dot 1 being right here. And then this is m dot 2. From that, and then the definitions of U1 and U2, which are the respective m dots divided by the rho, and then the cross-sectional area, pi over 4, and then the respective diameter to power 2. From these relations, this is all you can write, not only from the drawing, but from boundary layer theory. I want to make sure that we're on the same planet here. So, do you know who invented boundary layer theory? Who? Who? Very good. This other part of the stadium is silent. He is playing for the home team that just applauded. The rest of you have no reason to be applauded. Anyway, Prandtl. Prandtl, the same guy who had the student called Nikoradze, who painted the inside of the tubes with goop with sand grains in it, and figure out how wall friction depends on grain size. Yes, that kind. All right, so yeah, Ludwig Prandtl. And if you manipulate these expressions, by the way, the manipulating is explained in example number 4.1 in the textbook. In other words, today I'm beginning the lecture with one example of problem solving, okay? First, to solve a problem, first you have to invent the problem. So I invented the problem and now I'm solving it. For details, if what I put on the blackboard is not clear enough, you should read example 4.1. You find the following relations. First, that D1 over D2 is the same as writing L1 over L2, and then the two average velocities U2 over U1, everything to power 1/2. And in fact, I can label these things. In the textbook, these two are equation number 3. The upper ones are equation number 2. What I just wrote here comes from equations 2 and 3. And next, if these two expressions are called equations 5, then if you add to this equation 5, you obtain the surprising conclusion that L1 over L2 must be equal to 2. So it's the first time you find that the ratio of lengths is a clean factor 2, not 2 raised to a power that's less than 1. It turns out that a simple result rings a bell. And the bell is an image in the mind. It means that the drawing with which you began fits inside a square, because you see twice L2 equals once L1. So the drawing, and now I'm not drawing thick channels anymore because you know what L1 is. L1 is a thick channel, but that drawing fits inside a square. And so, yeah, okay, here's L1 and L2 and so on. In other words, if the flow is entrance flow in every duct, the rectangle of old, the best one, is actually a square. And where does this fluid go? By the way, the fluid is a heating agent. It's hot. It's heating this plate, the blackboard, which is cold. Well, here's the hot fluid coming in and leaving. Well, let's find out. Every new channel, meaning L2, is stem to its own pair of branches. So if I drew a square around L1, I can draw a square around L2. In other words, I'm generating a new pair of branches called L3. See that? And that means that at the top end, I have 2 L3s. And why not play this game at least one more time? Every new branch heats its own square. And gives birth to 2 new branches, each of size L4. So that means 2 branches here and 2 branches here. So the more you again travel mentally toward the smaller dimensions, the more the smaller branches multiply. And that is in the pursuit of greater access of this hot fluid on this piece of paper in which you make the drawing. let me draw more visibly what is being born here. It is a drawing that consists of sequential bifurcations. And then at this stage, two things must be said. If you imagine that this bifurcating can go on ad infinitum, meaning the number of such steps is without end, that big, without end, then the drawing is known as a fractal object. And this is a mathematical concept made famous by Benoit Mandelbrot. In the 1970s, leading to his book in 1982, I think it was. But that is not what's happening here. What's happening here is the fact that as you go toward smaller and smaller channels, the channels end up not being channels. And here is why. If you use these formulas, according to things you know, you can discover the progression of the slenderness of the channel. So the slenderness is the ratio of, for example, L1 over D1. This is the original slenderness. We know from early on that the relationship between D1 and D2 does not depend on the length. So we know that D1 over D2 is 2 to the power 1/3. And because L1 over L2 is known, you can construct the ratio of slendernesses and discover that that going from the original channel to the branches are not as slender. Meaning they look more like, no, anyway, they look more like shorter and shorter tubes, these entrance regions. And that means that as this number of bifurcation steps increases, the branches approach an ultimate branch that is no longer a channel. So the end or the largest value of n corresponds to the case where let's say ln over dn is 1. See that? Meaning that the idea of going toward the smaller and smaller dimensions hits the wall. And what is n? N is a very nice little exercise, also known as muscle flexing in the brain. So the question is, when is this idea good? At what point does it expire? First of all, let's find out ln, and then dn, and then divide the two in order to find the end value of little n. The ratio, or the smallness of the final channel length divided by the original, is the same as L2 over L1 times L3 over L2 and L4 over L3 all the way to Ln over Ln minus 1. How many of these factors do you have? You have n minus 1 factors. And certainly, see, these are the, remember when I taught you about technique? To go from the question to how you get the answer, you rely on technique. You rely on things that work. And this is a trick, but this is what you need to possess to get to the answer. And each ratio is equal to 1/2. You just found out. And that means that the answer here is 1 over 2 to power n minus 1, also written as L sub n is a lot smaller than L1, meaning L1 times this small number. So that takes care of the unknown numerator. The denominator is discovered the same way, meaning that the dn over d1 equals d2 over d1, and now dot dot, and then dn over dn minus 1. But each factor now is 2 to minus 1/3. And that means that the ratio, meaning this product of n minus 1 factors, is 2 to minus 1/3 to power n minus 1. And then these are the two ingredients, like the meat and potatoes in the soup. You make this ratio, and then you set it equal to 1. So this final aha, which I will call star, is written as when you make divide the ln divided by you make this ratio dn over L sub n, you get d1 over L1, and then 2 to power 2/3, and then n minus 1, where the right-hand side has information of how your drawing began. And the unknown n, when the drawing will end. And you get this n from this equation at the bottom by taking the logarithm of both sides. And the answer is that the n equals 1 plus 3 divided by 2, and then log of the original slenderness divided by log of 2. Okay, so how you begin the drawing? Perhaps with this size, the one I put on the blackboard, and then how many steps you have at your disposal until the smallest duct is a sac, not a duct. That sac is known as the alveolus in the lung. You heard about that. And of course, people take the alveoli for granted. But why should they happen? They happen for this reason, because the thorax is a finite volume in which the air enters as an arborescent flow, as a river delta, and it goes through this kind of natural behavior up to a point, and beyond that point, there is no more. That point is a sac, not a duct. And anyway, I calculated two values here. If the start is with a drawing in which L1 over D1 is 100, this is not unrealistic for the entrance region of something, then you find that this end value of n, and then n is equal to 11. If you're even more, let's say, courageous, you can imagine a shorter beginning, meaning a smaller one, L1 over D1 equals 10, and turns out to be 6. 11 and 6 are both numbers of order 10. So the number of bullets in your gun is pretty much fixed, okay? Even though the drawing starts very slender or not too slender. And this is how nature surprises you, because the whole thing, especially if you imagine this march toward infinity, looks complicated. But the natural way of things is to say enough, almost always, at the end of 6 bullets or so. Get it? And that is why the lungs of mammals, even though some are small, others are big, have comparable numbers of bifurcation levels. Certainly the lung in the mouse has something more like this. The one in the bigger animals, more such levels. In people, the number is 23. But all those numbers are of order 10, okay? Questions? So this was example 4.1. And the answer to the question of why should you worry about the entrance region has to do with heat transfer. Of course, a little bit later, it will address the question of where does this flow go? It cannot end up being stored in alveoli somewhere. There must be some holes in the blackboard through which these arrows, small arrows, are escaping. So that will be dealt with in the next chapter. But the alert to everyone is that in science, the ideas are very few. And in each chapter, you encounter maybe one new idea or self-standing idea, if you are lucky. And in chapter 5, you will rediscover things that have been put on the blackboard during the past 2 lectures, this being the second one.